So hello everyone, welcome to another video on discrete maths. In this video we are going to start a new topic called relation. Okay, this has got nothing to do with the kind of relation that boyfriend and girlfriends probably have, but this is another kind of relation. Uh, this is in maths. All right, so let us start this topic. It is called relation, and let us start with the definition of relation, right? So what is a relation? You already know what is a Cartesian product. I will not explain Cartesian product again. If you have any doubt, then go back and look at that video on Cartesian product. A Cartesian product essentially is a set that contains ordered pairs, right? Pairs that are of this form AB. Okay, so a relation is a subset of this Cartesian product. Alright, so more formally, let A and B be sets. So we have two sets A and B. A relation, a binary relation, okay, from A to B, okay, is a subset of the Cartesian product of A and B. So that is essentially a relation. So uh, we have this Cartesian product where we will have all these ordered pairs. Now ordered pair will be a pair. It will be ordered and it will contain two elements. The first element will be from set A and the second element will be from set B, right? And then every combination that is possible will be there in this in this Cartesian product. So out of all these Cartesian product, a subset of that we will take and we call that relation. Okay. Now two notations A or B. We use this notation when this ordered pair AB is in the relation. Okay. And A R is crossed off B. We use this notation to denote that this ordered pair AB is not in the relation. So relation is also essentially for all practical purpose. It's also a set. It's a set which is a subset of A cross B, A Cartesian product B. Okay. So uh, that is what relation is, and these are notations that we use to denote whether two elements A belonging to an ordered pair, whether this ordered pair is in the relation or not. Okay. This would indicate that AB is in the relation. This would indicate that AB is not in the relation. With that, here is an example of a relation. Okay. Here I have this set of students and I have this set of courses that we have. Alright. So these students are this Doraemon, Nobita, Shizuka, Sunio and Jian. Alright. You know these people, hopefully. And then the subjects are English, Maths and Science. Alright. So what this relation indicates is this, that this ordered pair AB, where A is a student and B is a course, will be in the relation if this student got a grade outstanding in that course. Alright. So what does this mean? This means that Doraemon, Nobita and Sunio, they got outstanding grade in English. Then Shizuka got outstanding grade in Maths and Science. Sunio got in English and then Jian got in Maths. So this directed edge, alright, this edge has a direction. This indicates that this and this are related. So we would say that in that relation where this ordered pair AB, where A was from this set and B was from this set, was in the relation if this student A got outstanding grade in this subject B. So we can say that Doraemon is in the relation English. Okay. So Doraemon got outstanding grade in English. Did Doraemon get outstanding grade in Maths? No. Doraemon did not get. Right. So we would write Doraemon did not get this outstanding grade. Is not in this relation with Maths. So we will say that this ordered pair belongs to the relation. This ordered pair does not belong to the relation. Alright. So yeah, this is essentially what relation means in discrete maths. Alright. So you need this knowledge about set. So with that knowledge you will have this knowledge about what is called uh, Cartesian product of set, and you know what is a subset. So a subset of this Cartesian product is a relation. This is an example of a relation. So we have, how did we represent this relation? This is a particular relation. What does this relation mean? It means that this set of students, and this is the set of subject, if some student A got outstanding grade in some subject B, then there would be a relation. Then that ordered pair would belong to the relation. Alright. So we represented this using a digraph, a directed graph. Okay. Then we could have represented this using standard set notation, that is your roster method. Alright. And then there is another notation. I want to show you another notation. Here, this is a matrix notation, and we will be looking at this matrix notation in far greater details in the next video. But right now, understand this. We have in the columns the name of the set B, the elements of the set B. Alright. And in this rows, along the rows, we will have the students. So Doraemon, Nobita, Shizuka, Sunio, and Jian. Alright. And then what will be there in this matrix? It will have Doraemon English is there in the relation. So I will indicate this with 1. Then Doraemon Maths is not there, Doraemon Science is not there. So this will be 0. Nobita English will be 1. Okay. Then Nobita Maths is not there, Nobita Science is not there. So this will be 0. Then Shizuka English is not there. So this will be 0. Shizuka Maths is there, Science is there. So this will be 1. Sunio English is there, rest of Maths and Science are not there. Jian Maths is there, English and Science are not there. So this is also one way of representing a relation. So this relation, this is the same relation. We could have represented it as a set. Alright. But then we will see set representation. But this is a digraph representation. This is a matrix representation. Alright. So remember this. Okay. Now let us talk about another relation without going too deep into that. Okay. Let us say we have these two sets A and B, and then A is the set of all the cities in India. Okay. B is the set of all the states of India. Alright. So we have two sets A and B. A is the set of all the cities in India. B is the set of all the states in India. The relation R. I am defining this relation as the set of ordered pairs AB, where A is a city and B is a state, and this ordered pair AB will belong to the relation if city A is in the state B. Alright. So what would that mean? That would mean that Guwahati, Assam would belong to this relation. I am calling it R, so it would belong to this relation R. But Guwahati, West Bengal would not belong to this relation R. Alright. So this ordered pair, it would be there in my Cartesian product. Alright. My Cartesian product will have every possible city state combination that is there, but it will belong to my Cartesian product, but it will not belong to my relation. This will belong to my relation. Why? Because my relation consists of those ordered pair which are in this form AB. Now there is a condition that I have. The condition is that my ordered pair will belong to my relation if this city is in this state. So this is true, so it will belong to this relation. This is not true, it will not belong to this relation. Similarly some other, say Ranchi, Bihar. this will not belong to the relation because Ranchi is not in Bihar, Ranchi is in Jharkhand. This will belong to the relation. Alright. So, yeah, this is what we have. This is what relation means. Don't think too deep about it. It's a very simple concept. There is no caveat as such. So, this is what relation is. Alright. So, let me give you another relation and let us try to represent it in the two ways that we saw. Okay. Now, this relation is between two sets A. So A has these elements 1, 2, 3, 0, 1, 2, and B is this set which has elements A and B. And what is my relation? Relation, of course, I said it can be represented as a set. Okay, so this is the representation in set. It contains the ordered pair 0A, it contains the ordered pair 0B, it contains 1A and 2B. Alright, so this is the set representation. Okay, these are the two sets. This is the relation that contains all this ordered pair. Now, I want to represent it using this directed digraph and the matrix method that we saw. So, let us do that. In digraph method, I will have this one set in this size, one set in the other side. So, the elements of this set A is here, the elements of set B is here. So I have 0A, so there will be this directed edge. I have 0B, so I will have this directed edge. Alright, I have 1A, so I will have this directed edge, and I have 2B, so I will have this directed edge. So this is this is the way to represent this relation in using directed graph. Alright, now let us represent it in matrix form. I have this set A along the columns, the elements of set A along the columns, the elements of set B along the rows, the elements of set B along the column. Alright. Now 0A is there, 0B is there, okay, 1A is there, 2B is there, rest of them are not there. So this is the representation in matrix form. Okay. Now in your book, you will see that they have done it in a slightly different manner. So this is the method that I would suggest that you follow, okay, because we will be using this representation at a later time. But in this particular problem, if you look at your book, instead of these zeros are not represented, and they have, instead of 1, they have represented it with cross. Alright, so they have done this. Instead of cross, we have written 1, and these blank spaces we have filled with 0. This is the way that we did is a better representation, and you will know why later on when we in the next video you will know why. Alright, so this diagram representation and matrix representation of this relation are between these two sets. Alright, so this is a representation. Okay, now next topic. Till now we have seen relation between two different sets, right? Now we are going to see relation among one particular set. And what do I mean by that? Relation on some set A. Okay, so till now we saw this relation between two sets A and B, right? So here when I say relation on a set A, I mean that both A and B are the same set. There is no set B, there is A. So it is a relation on a set A is a relation from A to itself. That means it is a subset of the Cartesian product of the set n itself. So Cartesian product of A cross A. Alright. And the relation will be a subset of itself. So let us let me explain this with an example. Okay, let us say I have this set A and it consists of 1, 2, 3, 4. Okay, so what will A cross A contain? A cross A will contain this 1, 1, 1, 2, 1, 3, 1, 4, then 2, 1, 2, 2, 2, 3, 2, 4, and so on. 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, and 4, 4. Okay, I am not writing this down. You know what this is, you know what a Cartesian product is. Now, this is the Cartesian product. This would have been all the possible ordered pairs when I have a relation, when I have this Cartesian product of A to itself. Alright. So, our relation will be a subset of this Cartesian product. Okay. So, let me give you a relation. This R contains all these ordered pairs AB such that A divides B. Alright. So this is the relation that is defined. Okay, and then this is my set A. So here is the question: what are all the ordered pairs that are there in the relation? Let us find the relation. Okay, so the relation will contain. It will contain. Does 1 divide 1? Yes, 1 divides 1. 1 divides 2. 1 divides 3. 1 divides everything, right? 1 divides 4. Okay. Then does 2 divide 1? Perfectly. No, it does not. So 2, 1 will not be there in the relation. Does 2 divide 2? Yes, it does. Does 2 divide 3? No, it does not. Does 2 divide 4? Yes, it does. It will be in the relation. 2, 3 will not be in the relation. 2, 4 will be in the relation. What about 3, 1? It does not. 3 does not divide 1. 3 does not divide 2. 3 divides itself. It will be in the relation. 3 does not divide 4. 3, 4 will not be there. What 4, 1, 4, 2, 4, 3 will not be there. Because 4 does not divide 1, 4 does not divide 2 or 3. Okay, 4 divides 4. So 4, 4 will be there. So this is an example of a relation. Okay. Now this is an example of a relation on a set. So this relation is not between any two other sets. The elements are not from two different sets. The elements are from the same set, right? Both A and B are from the same set. So we call this relation on a set. Okay. Well, the next thing that we are going to see are a few properties of relation. Okay, I hope you understood up to this point. If you did not, then of course you can contact me through various means, like you can WhatsApp me, you can write a comment on the comment section below. Next topic is properties of relation. Alright, so let us look at the first property, reflexive. Okay, a relation R on a set A is called reflexive if for all the elements this ordered pair AA belongs to the relation. If this condition is satisfied, then the relation is called a reflexive relation. Okay, this is very easy. When I have a matrix representation of the relation, this AA, BB, CC, those will all be along the diagonals, right? So if I have this set with 4 elements, say A, B, C, D, this will be the matrix representation. If all these are 1, AA, BB, CC and DD, If all of these are 1, then we say that the relation is reflexive. Alright. Then the next definition, symmetric. Symmetric means for all A and for all B, if AB belongs to the relation, then BA must also belong to the relation. What does this mean? I have written AB. I am using AB over here and AB over here as well. So let me not do that. Let me use different variables over here, the different elements over here. Let me use numbers instead. Okay. So what does symmetric means? Symmetric means that if I have some element, okay, in the relation, if I have this ordered pair 0, 2, it means that 2, 0 should also be there. Okay. If for every element, say 3, 1 is there, then 1, 3 is there, then 3, 1 should also be there. Okay. So it implies that if there is some AB in the relation, then BA should also be there. Okay, we will see all of this with more examples. Next is antisymmetric. Antisymmetric, let me define it first. For A implies, for all A and for all B, if AB belongs to R and BA belongs to R, then it implies that A is equal to B. That means this is a symmetric relation, right? Here, if this AB, this 0, 2 is there, then 2, 0 is also there. Okay, this would be symmetric, but this is not antisymmetric. Why? In antisymmetric, if this 0, 1 is there, then 1, 0 cannot be there. Okay. If some AB and BA, both of them are there, that means A is equal to B. That means only along the diagonals we can have that thing. This 1, 1 is there and 1, 1 is there. So obviously. Okay. But apart from that, if I have this 0, 2, I cannot have this 2, 0. Okay. If I have this 3, 1, I cannot have this 1, 3. Okay. So if I have 3, 1 and 1, 3, then that would not be antisymmetric. Now remember this thing. Symmetric and antisymmetric are not opposites. A set can be both symmetric and antisymmetric. A set can be neither symmetric nor, a relation can be both symmetric and antisymmetric. Some other relation, it can be neither symmetric nor antisymmetric. Alright. So it is not necessary that if a relation is symmetric, it is not antisymmetric, or if it is antisymmetric, it is not symmetric. That is not true. Okay. So these are not opposites. Alright. So remember that. Now this is symmetric, this is not antisymmetric. Had this not been there and say this not been there, this would have been symmetric. Okay. So see, 2, 0 is there. So 0, 2 is not there. 1, 3 is there. 3, 1 is not there. Okay. So this is, of course, in this matrix, everything that I did not write, these are all zeros. Okay. This is antisymmetric. Now one thing, notice here along the diagonals, I have all these ones. If I don't have some 1, this is not a problem. Okay. What about this? This 2, 2 is there. If I go 2, 2, this is also there. This other direction, if I come 2, 2, that is also there. Okay. So it is possible only if this A is equal to B. Okay. So I have A equal to B, so 2 is equal to 2, that is not a problem. If I have along the diagonals I may have 1, and apart from the diagonals, if I have some 1 in some other place, in its mirror location I cannot have a 1. Okay, if I have a 1 over here, then in antisymmetric I cannot have a 1 over here, I will have to have a 0 in here. Okay, so think about it. How many possibilities can we have for these two pairs? How many possibilities can we have? We can have this, right? This 3 0 is 0, this 0 3 is also 0, that is not a problem. Okay, 3 0 and 0 3, both of them are not there, that is not a problem. But if 1 3 is if 3 1 is there, then 1 3 cannot be there. Okay, so there are three possibilities for this thing. This is directly related to this, right? This is dependent on this. 1 3 is dependent on 3 1. So it may be possible that 3 1 is there and 1 3 is not there. That is one possibility. Another possibility is 1 3 is there and 3 1 is not there. Second possibility. And the third possibility is that none of them are there. Okay, both 1 3 and 3 1 is not there. So for this particular cell, and this is dependent on this, I have three possibilities. Either this will be there and this is not there, or this is there, this is not there, possibility 1. Possibility 2, this is there, this is not there. Possibility 3, both of them are not there. Okay, so for each of them, three possibilities are there. So don't worry about that. We will come back to this topic at the end of this video. Okay, so this is antisymmetric. Next definition is transitive. This means that for all A, all B and all C, if AB is in the relation and BC is in the relation, that would mean that AC should be in the relation. Okay. So yeah, once again going to this 0, 0, 1, 2, 3. 1, 2, 3. Say 0, 1 is there, then 1, 2 is there. Okay. So I have 0, 1 and 1, 2. This relation will be transitive if for every such pairs 0, 1 and 1, 2, then 0, 2 should also be there. Okay. This and this being in the relation implies that this would also belong to the relation. Okay. So for any AB being in the relation and BC being in the relation, transitive property means that in that relation for every such pairs, this AB then BC means AC should also be there. This is transitive. Alright. Now let us try to see if we could figure out if some of this relation, okay, let me write down a few relations, if they are reflexive, symmetric, antisymmetric and transitive. So relation 1, I will write down a few relations. It consists of 1 1, 1 2, 2 1, 2 2, okay, then 3 4, 4 1 and 4 4. Then another relation R2, this consists of 1 1, 1 2, then 2 1. Then R3, 1 1, 1 2, 1 4, 2 1, 2 2, 3 3, 4 1 and 4 4. Then the final relation R4. R4 consists of 1 1, 1 2, 1 3, 1 4, 2 2, 2 3, 2 4, 3 3, 3 4, and 4 4. So I have these four relations. Now, is this symmetric, asymmetric, uh, reflexive, transitive? Can you answer? No, there is data missing. I still did not tell you what is the relation on. This relation on some set, right? I need to tell you whether what are the elements on the set. Otherwise, you will never know. You may have 1 1 2 2 3 3, and you will think that it is reflexive. But then, if the set consists of 4 elements, okay, so 1 2 3 4, then 4 4 is not there. So, without knowing what is in the set, answering whether a relation is something, whether it satisfies some property, that is meaningless. Okay, so my set is this set 1 2 3 4. All right, with that, let us figure out if each of this is reflexive, symmetric, antisymmetric, and transitive. Is this reflexive? So reflexive, symmetric, antisymmetric, and transitive. We will try to figure out for these 4 different sets that we have. Right, 4 different relations that we have. Okay, this one, is it reflexive? 1 1 is there, 2 2 is there, 3 3 is not there, so it is not reflexive. What about this? 1 1 is there, 2 2 is not there, 3 3 4 4, those are not there, this is not reflexive. What about this? 1 1 is there, 2 2 3 3 4 4, all of them are there, so this is reflexive. What about this? 1 1 2 2 3 3 4 4, all of them are there, so this is reflexive. Okay, next let us find out if this is symmetric. 1 1, not a problem. 1 2 is there, so 2 1 is also there. Okay, then 2 1 is there, 1 2 is there, 2 2 2 2, 4 3 is there, 3 4 is there, but 4 3 is not there. Okay, so this is not symmetric. What about this? This 1 1 is there, implies 1 1 is there, not a problem. 1 2 is there, implies 2 1 is there, so good. 2 1 is there, implies 1 2 is there, so good. This is symmetric. So for every AB, BA is there. For every AB, BA is there. Okay, so this is symmetric. Let us look at this. 1 2 is there, 2 1 is there, good. 1 4 is there, 4 1 is there, good. 2 1 is there, 1 2 is there, good. 2 2, not a problem. 1 1, not a problem. 1 1 is there means 1 1 is there. So with this we don't have much problem. 3 3 is there, means 3 3 is there. 4 1 is there, 1 4 is there, and 4 4 is there. This is also symmetric. Let us see in this. 1 2 is there, 2 1 is not there. Okay, so this is definitely not symmetric. Next, let us try to find whether these are asymmetric. Okay, asymmetric means this one, if AB is there and BA is there, then A must be equal to B. Okay, but let us see here. One AB is there and BA is there. 1 2 is there and 2 1 is there. But is 1 equal to 2? No. So this is not asymmetric. Okay, let us look here. This 1 2 is there, 2 1 is also there. So 1 2 is there, 2 1 is there. Is 1 equal to 2? AB is there, BA is there. Is A equal to B? Is 1 equal to 2? No. But then this is satisfied. 1 1 is there and 1 1 is there. Okay, we can say this is AB and we can say this is BA. Okay, AB is 1 1, BA is 1 1. Both of them are there. Then A is equal to B. 1 is equal to 1 in this case, right? So in this case, that is not a problem. These elements or the diagonals being there is not a problem. Okay. Let us look at R3. 1 2 is there, 2 1 is there. So AB is there and BA is there, but then A is not equal to B, 1 is not equal to 2. Or say 1 4 is there, 4 1 is there. AB is there, BA is there, but A is not equal to B, 1 is not equal to 4. So this is also not antisymmetric. Let us look at this one. 1 1 is there and 1 1 is there, but 1 is equal to 1, so that is not a problem. 1 2 is there. Is 2 1 is 2 1 in there? No. 1 3 is there. Is 3 1 in there? No. 1 4 is there. Is 4 1 in there? No. 2 2 is there, but then 2 is equal to 2, not a problem. 2 3 is there. Is 3 2 in there? No. 2 4 is there. Is 4 2 in there? No. 3 3, not a problem, because 3 is equal to 3. 4 3 is there. Is 3 4 is there. Is 4 3 in there? No. And 4 4, 4 equal to 4, not a problem. So here, if any AB is there, then unless and until A is equal to B, for example this, in this case, and this case, A is equal to B. So if AB is there and BA is then unless A is equal to B, then BA is not there. Right? So if 1 2 is there, then 2 1 is not there. If 1 3 is there, 3 1 is not there. So this is antisymmetric. I hope you understood what is meant by antisymmetric. Alright, it's easy, but then take care. Alright, read the definition, you will understand. Okay, let us now see whether all of these are transitive. Okay, 1 1 is there, 1 2 is there, so 1 2 is there. Okay, 1 1 2 1, 1 1 is there, 1 1 2 2, 1 2 is there, then 1 is gone. 1 2 2 2, 1 2 is there. 2 1 1 1, 2 1 is there. Then let us see. Okay, 3 4 is there, 4 1 is there. Okay, is 3 1 is in there? So AB is there, BC is, this is A, this is B, 4 is B, 4 is B, this one is C. So AB is there, BC is there. Is AC there? Is 3 1 in there? 3 1 is not there, right? So this is not transitive. Okay, let us look in here. So 1 1 1 2, 1 2 is there. Then 1 2 2 1, 1 1 is there. 2 1 1 2. See, I have 2 1 and then 1 2. All right. This is A, B. This one is B. Then this, I'm saying C. Okay. So 2 1 is there. 1 2 is there. Is 2 2 in there? 2 2 is not there, right? So this is not transitive. Okay, next one. Is this transitive? 1 2 is there, 2 1 is there, 1 1 is there, right? 1 1 4 is there, 4 1 is there, 4 4 is there, 1 4 is there, 1 1 is there, so not a problem. 2 1 is there, 1 2 is there, but 2 2 is not there. Oh yeah, 2 2 is there, not a problem. Then let us see. 1 4 4 1. Okay, we have to check for everything, right? So that is that part. 1 1. Okay, let us check systematically instead of trying to figure out too fast. Let us check systematically. 1 1 and 1 2. 1 2 is there. 1 1 and 1 4. 1 4 is there. 1 1 and no other thing starts with 1. 1 2. 1 2 and 2 1. 1 1 is there. Okay, 1 2 and 2 2. 1 2 is there. So no other thing with 2. 1 4. So let us check with 4. 1 1 1 4. 1 1 is there. 1 4 4 4. 1 4 is there. Then 2 1. Let us start with 1. 2 2 1 is there. 2 2 is there. 2 4 is not there. Alright. So let us see. This is A, B, this is B, this is C. Okay. So I have this AB. 2 1, I have this BC 1 4, 2 1 is there, 1 4 is there, but 2 4 is not there. Alright, so this is not transitive. Okay, so we have to check systematically. Transitive will take the highest amount of time because you have to check with all these different ordered pairs. Alright, if it is given in this form. Transitive is very easy when you have this diagram. Okay, we will see later on. So it depends on representation. If your set is too big, later on I will tell you that do one thing, change it to a different representation. Okay, then you will be able to work with these things far faster. Okay, we will talk about that in the next video. Let us continue. Let us check whether this is transitive. So 1 1 1 2. So 1 2 is there. 1 1 1 3 1 3 is there. 1 1 1 4 1 4 is there. So if we have this 1 1 and we check with something, that thing itself will be the transitive element, right? So yeah, don't worry. 1 2 is there, then 2 2 2 1 2 2 2 1 2 is there. 1 2, then 2 3 1 3 is there. 1 2 and 1 4. Sorry, 1 2 and 2 4 1 4 is there. Then 1 3, they have check with 3 1 3 and 3 3 1 3 is there. 1 3 and 3 4 1 4 is there. Okay, so 3 is done. 1 4, let us check with 1 4. So 1 4 and 4 4 1 4 is there. Good. Now let us do in this 2 2 2 2 and 2 3 2 3 is there. 2 2 and 2 4 2 4 is there. 2 3, let us check with 3 2 3 and 3 3 2 3 is there. Okay, 2 3 and 3 4 2 4, is 2 4 there? Yes, 2 4 is there. So done. Now 2 4, let us check with 4. Okay, this is the reason why we check with 4, because the last and last of this we have to check. 2 4 is there, 4 4 is there, so 2 4 is there. Now let us check with 3 3 3. So let us check with 3 3 3 is there, 3 4 is there, so 3 4 is there, not a problem. Then let us check with this 3 4 3 4 is there and 4 4 is there, so 3 4 is there. Okay, we have finished checking all of them. All the transitive elements that are supposed to be there are there, so this is transitive. Okay, good. It took some time to find out whether all of these are transitive, but then the rest of them are easy, right? Okay, so let us do one more. I have this set, this divide relation on a set. What is my set? Set of, my set is this, set of integers, alright, set of positive integers, and my relation is given by this, relation AB such that A divides B. Okay. Now, is this reflexive? Okay. So all these positive integers, do they divide themselves? 1 divides itself, correct? 2 divides itself, 3 divides itself. So 1 1 is there in the relation, 2 2 is there, 3 3 is there. So all these positive number, they divide itself. Okay. So this is reflexive. All this AA, where A is a positive number, is there in the relation. So this is reflexive. Is it symmetric? Okay. So symmetric means if AB is there, then BA should also be there. So AB, let us say A is 2, B is 3. So 2 divides, A is 2, B is 4. So 2 divides 4. So 2 4 is in the relation. Does 4 divide 2? Perfectly, it does not, right? So 2 4 is in the relation, but 4 2 is not in the relation. So this means that there is this AB that is there in the relation, but then BA is not there in the relation. That means it is not symmetric. Now, is it antisymmetric? So if what is antisymmetric? Apart from these diagonal elements, this 1 divides 1, 2 divides 2, 3 divides 3. Okay. If some A divides B, then is it possible that B divides A? If 2 divides 4, then does 4 divide 2? If 3 divides 9, then does 9 divide 3? Is it possible that some A divides B and B also divides A? Okay. It is only possible when A is equal to B, right? So because of that, we know that this divides relation is antisymmetric. Now, is it transitive? Now say A divides B and B divides C, then does A divide C? Okay, simple question. This is, we know from fundamental theorem of arithmetic, we know that this is true. If some A divides B, okay, then AB is in the relation. If B divides C, then BC is in the relation. Okay, the question is AC in the relation? So A divides B, B divides C. Does A divide C? Yes, it does. Right. So 2 divides 4, 4 divides 8. Then does 2 divide 8? It does, right? So this is transitive. Okay. So this was another example. Now let us look at one final topic and then we will be ending this video. Okay. We are going to count the number of relationships. Okay. How many relations are possible on a set with n elements? Okay. That is the question. How many relations are possible on a set with n elements? So what is a relation? A relation is a subset of the Cartesian product, right? So how many elements may be there in the Cartesian product? The Cartesian product of n elements, say as this set A has n elements, so Cartesian product will have n square elements. So how many relations are possible? Relations is how many subsets are possible of this set A cross A. A cross A has n square element. We know that the number of subsets is the cardinality of power set. Alright. So 2 to the power if I have m elements in the set, then 2 to the power m would be the number of subsets of that set, right? So in our relation we will have in our this set A with n number of elements, we will have a total of 2 to the power n square number of relations that are possible. Why? Think about it. A has n elements, A cross A has n square elements. How many subsets are possible of this n square of this set? 2 to the power n square. Why? If my set had m elements, then I may have 2 to the power m subsets. Here I have n square elements, so I have 2 to the power n square subset. So all these subsets are different relations. Right? So we know all these subsets of this set A cross A are all these different relation. That is the definition of relation. So we know this is the number of relations that we have. But this is a good way of thinking. Let me explain using another method. This is my matrix representation, right? In this matrix representation, I have n elements in this column, along the columns, n elements along this column. So how many cells do I have in this matrix? This matrix will have if you have difficulty multiplying, then go ahead and add this up. I have n plus, if I keep on adding n times, and if I keep adding n times, then I will have total n square different cells. Right? Now n square different cells. Each of them cell, it can be in the relation. Each of them can be in the relation or may not be in the relation. So each of this cell may take a value of 1 or 0. So each of this cell I will have two choices, right? 1 or 0. So I will have two choices for this cell, into two choices for this cell, into two choices for the next cell, into so on. How many cells are there? For each of them I will go on having two choices up to how many of these are there? There are a total of n square. So I am multiplying 2 n square number of times. So I have 2 to the power n square. Okay, this is the number of ways in which I can fill this matrix. Okay, I can have all of them 0, I can have all of them 1, and I can have anything in between. So these are the total number of ways in which I can fill a n cross n size matrix where I can fill them with only two values. Okay, if I were able to fill this with three values, then it would have been 3 to the power n square. Okay, we saw this in this product rule. Okay, it is not that I will choose fill this or I will fill this. I will fill this and then I have to fill this, then I have to fill this. It is an and relation, it's not a or relation. So we have to apply this product rule, not the sum rule. Okay, we already talked about this. So if you have forgotten, look up your book. We did it back before this coronavirus lockdown, so there is no video, unfortunately. You will have to look up in your book if you have forgotten what is sum rule and product rule. But then remember this, I have to fill this and then I have to fill this and then I have to fill this. It's a and relation. Okay, it's not that I fill this or I fill this. Okay, I have to fill one after another. There is a and relation, so there is a multiplication, not sum. So how many choices do I have in each position? I have two choices, so it's 2 into 2. How many places do I have to fill? There are n cross n square places do I fill. So I multiply 2 n square number of times. If I multiply 2 10 number of times, it's 2 to the power 10. I am multiplying 2 n square number of times, so it's 2 to the power n square. Okay, simple. Okay, this is the total number of relations that I may have on a set A with n elements. My next question is this: how many relations may I have on a set A with n elements such that the relation is reflexive? Okay, so relation on set A, number of relation on set A that are reflexive. Okay, let us think about it, what is happening. I have this 1, 2 up to n. I have this 1, 2 up to n. What does it mean for a relation to be reflexive? It means that all this AA, okay, should be there in the relation. So this should be there in the relation, this is there in the relation. Along these diagonals, all of these elements are there in the relation. Okay, so all of these are fixed. We do not have any choice over here. Along the diagonals, since these relations are reflexive, so our diagonals are fixed. How many elements do I have along this diagonal? I have this 1, 2, 3, 4. So in every row I have one element in the diagonal. So I have n number of rows, I have n number of elements along the diagonals. Alright. So these n cells in my matrix are fixed. They have to be 1. Otherwise it will not be a reflexive relation. Alright. So along these diagonals they are fixed. What was the total number of cells that I had? I had n square number of cells. We just discovered that if you in the last this finding number of relations, we had n square. Out of this in the reflexive, n will be fixed. This along the diagonals, these n elements are fixed. The rest of them I can fill with 0 or 1. Right? So I can fill with 0, I can fill with 1. I don't know what I'm going to do. All these different things that I can do. Okay, filling with 0, 1, filling the first cell with this 1, 1, 2 with 0, 1, 3 with 1. So lots of things I can do. Okay. So how many cells are there where I can make these choices? Okay. There were total n square number of cells. Out of these n cells, I do not make any choice. Why? Because they are fixed. Why are they fixed? Because these relations are reflexive. So along these diagonals, this n number of cells are fixed. That leaves me with n square minus n cells where I can make choices. Now, how many choices do I make in each of them? I make two choices, whether I fill with 0 or I fill with 1. So that means I will have this 2 into 2 into 2 how many times? This many times, right? Because these are the number of places left that I can fill. That means I have 2 to the power n square minus n number of places, right? Number of cells that I can fill. So this number of cells that I can fill, that means these are the total number of relation on a set A. A has cardinality equal to n. That means A has n elements. So relation on set A that are reflexive. So these many relations I can get that are reflexive. So these many reflexive relations are possible. Alright? Okay. Next, let us try to figure out how many of them are symmetric. Okay. Question. How many of them are symmetric? Let us try to figure out let us try to remind ourselves what is symmetric. What does symmetric mean? Symmetric means that if I have 1 in here, okay, then this will be, if 1, 2 is filled with 1, then 2, 1 must also be 1. Okay. If 1, 2 is 0, then 2, 1 must also be 0. Okay. So I cannot have 1, 2 is equal to 1 and 2, 1 is equal to 1. Then what will happen? This AB will be there, but then BA will not be there. Otherwise, if I have this 1 and this 0, this 2, 1 will be there, then 1, 2 will not be there. This is not allowed in a symmetric relation. The definition of symmetric relation, it says that if there is some AB in the relation, then BA should also be in the relation. That means if 2, 1 is in the relation, then 1, 2 should be in the relation. If 1, 2 is in the relation, then 2, 1 should be in the relation. So I cannot have a 0 in here and 1 in here, or a 1 in here or a 0 in here. So if I have a 0 in here, this should be 0. If I have a 1 in here, this should be 1. Okay. Only along the diagonals they are independent. The rest of this lower triangular matrix will be a mirror reflection of this part. Whatever I write in this will reflect in here. So I don't really have a choice over here. Okay. This will automatically get filled. This, if my relation is symmetric, then this 2, 1 will automatically get filled when I fill this 1, 2. If I fill this 1, 2 with 0, then this will get filled with 0. If I fill 1, 2 with 1, this will get filled with 1. So I don't really have a choice over here. Alright. So my question, how many relations on this set A is possible that are symmetric? Okay. So how many places that are there that I can fill? These diagonals I can fill, and this rest of them I can fill. The upper triangular matrix I can fill. So in this row, how many positions are there that I can fill? There are n positions. In this row, how many are there that I can fill? This one is gone. This will depend on this. So I have n minus 1 position. In the third row, how many positions? These 2 are gone. This 2 will depend on, this 3, 1 will depend on 1, 3. And this 3, 2 will depend on, 3, 2 will depend on this one, 2, 3. 3, 1 will depend on 1, 3. and then 3 2 will depend on 2 3, right? Yeah, so this 2 will depend on this 2. Okay, so here these 2 are gone, I don't have any choice with this 2, so this leaves me with n minus 2 places that I will have a choice. This will go on until in the last row I will have only one choice, this in the diagonal, the last element. Okay, so how many places are there in total where I can fill? See, this rest of them will be filled automatically as soon as I fill this part, right? This being 1, if I put 1 and 1 in here, then this will be filled with 1 and 1. Okay. So how many places do I have where I can fill? Here I will have n, here I will have n minus 1, here I will have n minus 2, I will go up to, here I will have 2, then 1. So this many places in each row, this in this row, this in this row, this in this. So this many are there in total. Okay, so I will add all of them, n in here plus n minus 1 in here, then n minus 2 in here. So all these places are there that I can fill. What is the total? It is the 1 plus 2 plus 3 plus 4 up to n. So this is basically 1 plus 2 plus dot 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 up to n. So this is the sum of the first and natural number, right? This is n plus 1 by 2. Okay, so these many places are here, okay, including the diagonal. I remember this is symmetric. Okay, I can have the diagonal, I can fill with this, I can have 1, I can have 0. This is not reflexive. There is no mandatory that my diagonal has to be filled with 1. It can be filled with 1, it can be filled with 0, my diagonal, right? So it is not reflexive, it's just symmetric. So all these places I can fill with 0 or 1. Okay, I have this choice. How many places are there in total? We just figured out there are this number of places in total. Okay, so how many total number of relations are can be there that are symmetric on this set A that has n elements? It will be this many places, 2 into 2 into how many times? This many times, because this many places are to be filled. So it will be 2 to the power n plus 1 by 2. Okay, so this many relations, this many symmetric relations can be we can get from a set A that has n number of elements. Okay, so this is symmetric. I hope you understood everything. All right, this might be a bit confusing, but then go back, watch this portion of finding number of relation from the beginning. I hope you will understand. Next, let us try to find out the number of relation on a set A that are anti-symmetric. Okay, don't proceed if you have doubt in finding the number of relation that are symmetric. You have to be clear with that. Okay, now let us try to find the number of relations that are anti-symmetric. I have once again n number of columns, n number of rows, because there are n number of elements in my set. Okay, so this is the matrix representation. Now what are the things that I may have? What is antisymmetric? Okay, along the diagonals I may have 1 or 0, not a problem. I may have along the diagonal, I may not have. This is not reflexive, so there is no rule that the diagonal element have to be there, not a problem. I am free with the diagonals. Okay, that leaves me with things apart from the diagonal. Okay, let us talk about this 2 1. This, if I have 1 in here, so 1 2 will have to be 0. Okay, if I have a 1 in 1 2, this 2 1 will have to be 0. So one possibility is 1 2 is equal to 1 and 2 1 is equal to 0. Another possibility is 1 2 is equal to 0 and 2 1 is equal to 1. Third possibility is both of them can be 0. 1 2 is equal to 0 and 2 1 is equal to 0. Okay. So when I make this choice for this, I will kind of influence this also, but then like in symmetric, when I wrote a 0 in here, this automatically became 0. When I wrote a 1 in here, this automatically became 1 in symmetric. Here I may have 1 in here, then this should be 0. I may have 1 in here, then this should be 0, or I may have 0 in both the places. So think about it. If I take these two as being linked, as being one place that I can fill, okay, then there are three choices that I can make for this pair. I will consider them to be a pair, one place. Okay, then there are three choices that I can make. So this kind of, we will not call it dependent, this is pseudo dependent. It is a term that I am using. Right? This is not a term from your book, but I am calling it pseudo dependent on this. Okay, kind of dependent on this. So how many places are here? This diagonal I can have, here I can have anything. This is not dependent on any other place. This is not dependent on any other. This is not dependent. So along these diagonals I have n places that are not dependent on any other. Okay. So this, along the diagonals I may have these n places that can be anything. That can be 1 or 0. So I have, along the diagonals I will fill for the first position I have two choices, 1 or 2, 0 or 1. For the second I have two choices, 0 or 1. And like this I have, for the n places I have n choices, n places that I can fill with two choices for per place, right? 0 or 1. So two choices into two choices into two choices on this diagonal I have n places. So 2 to the power n ways in which I can fill the diagonal. Okay. So along this diagonal I can have this many choices. Now apart from the diagonal, that is the main thing. How many do I have? This I am saying this lower triangular matrix is dependent on the upper triangular matrix, pseudo dependent I say. So how many places in here? If I leave the diagonal, I have n minus 1. I will make the choice for the diagonal extra. I will fill the diagonal and then I will fill the other things. Okay. So this many way to fill the diagonal. How many ways to fill the rest of the places? I have to count the rest of the places, right? So these are the diagonal. Here I have this n number of elements minus the diagonal element, that leaves me with n minus 1. Here I will have leave this and the diagonal. So 2 I will leave, so n minus 2 and so on up to here. What will be here? There will be nothing. Okay. So only diagonal was there, but then diagonal also I am removing. I make choice for the diagonal extra. So this is 0, this is 1. So how many places are there? All these places. Apart from the diagonal and the lower triangular matrix. Why I am leaving this diagonal? Because diagonal is independent. I can fill with it 0 and 1. Diagonal does not depend on any other. Because diagonal is AB, where A and B is both equal. So diagonal AB, BA, A is equal to B. Diagonal is independent. Okay, the rest of the places depends on the definition. AB is not equal to BA in the rest of the places. 1, 2 and 2, 1. 1 is not equal to 2. Right. So here I subtract the diagonal. Rest of them I have n minus 2. Here I have n minus, I have n minus 1. Here I have n minus 2. So on up to 2, 1, 0. So how many total places are here? This is n minus 1 plus n minus 2 plus n minus 3 up to 2, 1 and 0. So how many in there total? I have to add them, right? This will be 1 plus 2 plus up to n minus 1. Sum of first n minus 1 natural number. So n minus 1 into n by 2. This many places are there, right? Now each of these places is linked with some other. It's mirror image, so this is linked with this. Each of these places, how many choices do I have? I can have this. This can be 1, this can be 0. Choice 1. I can have this. This can be 1, this can be 0. Choice 2. Or I can have this. Both of them are 0. So I have 3 choices for each of these cell. Okay. So I have 3 to the power this. Many ways in which I can fill this upper triangular and lower triangular minus the diagonal. Okay. So I have this many ways to fill the diagonal, this many ways to fill the rest of the matrix. Alright. So how many ways in total? Do I add them? Do I fill the diagonal or fill the rest? Or do I multiply them? Do I fill the diagonal and then fill the rest? Or I fill the rest and then I fill? I have to do both of them. I have to end this and that. Right? I have to do both of them. I have to multiply. It is not done this or that. Whether I fill the diagonal or I fill the rest. It is not a or. This is the and. So it will be, the product rule has to be applied over here. So total, how many choices will I have? I will have 2 to the power n ways to fill the diagonal multiplied by 3 to the power n into n minus 1 by 2 way to fill the rest of the matrix. Alright. So this many relations are possible on a set with n elements that are antisymmetric. The relation is antisymmetric. So this many way. I hope you understood this. This was the most complex thing. Now apart from this, there is transitive, but then transitive is beyond the course. There is no such beautiful formula for transitive. Alright, so I hope you have understood everything in this video. If not, you can go ahead, contact me using WhatsApp, email, or you can write your doubt in the comment section below. I hope you understood. In the next video we will continue with relation and we will do more things with relation. So see you in the next video. Thank you.